James Webb was built to look deeper into the universe, but it may have found something that should not exist: a distortion of light in empty space, with no visible mass to explain it. If confirmed, this signal could break the cosmic model scientists have trusted since Einstein and point to a hidden boundary beyond our own universe. Today, we explore why James Webb's strangest detection may be the first sign of a different universe. Before we go deeper, please take a moment to like and subscribe. It costs nothing, but it truly helps support the channel. Now, let's begin. The James Webb Space Telescope captured a region of space confirmed to be completely empty. No galaxies, no gas, no dust, and yet light passing through that void was still bent. Not slightly, not ambiguously. Bent? That single fact breaks something that has held for over 100 years. In 1915, Albert Einstein published his general theory of relativity. Among everything it predicted the slowing of time near massive objects, the expansion of the universe, the existence of black holes. One prediction became the cornerstone of modern astronomy: mass curves space-time, and curved space-time bends light. No mass, no bend. That equation has held without a single exception for over 100 years. Every gravitational lens ever observed, every warped image of a distant quasar, every distorted arc of ancient starlight we have ever catalogued, all of it obeyed that rule. Perfectly, consistently, every single time. Until now, the idea that light bends around mass is not exotic theoretical territory. You already understand it intuitively, even if you have never thought about it in those terms. Hold a magnifying glass over a piece of paper on a sunny afternoon. The lens bends light to a focused point, not because the glass is pulling light with some invisible force, but because the glass changes the path light travels through. Einstein's revelation was that mass does the same thing to the fabric of space itself. When light from a distant galaxy passes near something enormously heavy, another galaxy, a cluster of galaxies, a dense concentration of dark matter space around that mass, curves like a depression in a stretched rubber sheet. Light follows that curve. The result, seen from a telescope, is a distorted arc, a ring. Sometimes multiple ghost images of the same object smeared across the sky, like reflections in a funhouse mirror. Astronomers call this gravitational lensing. It is one of the most reliable, most reproducible phenomena in all of observational cosmology. Every single example ever recorded has had one thing in common. Something was there, something with mass, something that bent the fabric of space. What James Webb recorded was different. Fundamentally, structurally, disturbingly different. The signal appeared in a region of sky classified in survey catalogs as a cosmic void, a large-scale emptiness. The kind of structure that forms naturally in the universe's web, where matter has drained away into surrounding filaments over billions of years. This specific region had been cross-checked against galaxy catalogs, radio surveys, and X-ray observations before Webb ever pointed at it. Nothing. Not a faint smear of a distant galaxy. Not a wisp of intergalactic hydrogen. Not the thermal signature of a gas filament too cold to glow brightly. The emptiness had been confirmed from multiple angles, across multiple wavelengths, and then Webb pointed at it. What came back was not the undisturbed, straight line passage of background light that empty space should produce. The light was bent. But the geometry of that bending, and this is the detail that stopped the analysis teams. Cold was unlike anything in the entire catalog of known gravitational lenses. Every standard gravitational lens produces curves, arcs, rings. The distortion bows outward from a central mass, symmetric the way gravity is symmetric, fading as you move away from the center. The shape encodes whatever caused it, the way a shadow encodes the silhouette of whatever blocked the light. This signal was flat, not curved around a central point, not tapering at the edges. A long, extended, geometrically precise, linear distortion stretching across the field of view with an evenness that has no analog in the entire documented history of gravitational lensing observations. Not approximately flat, not mostly flat, flat in a way that, to the researchers first examining the data, looked almost artificial in its regularity. The observation was captured in the near-infrared wavelengths of Webb's NIRCam instrument, specifically in the 1 to 5 micron range, the same range that allows the telescope to pierce cosmic dust and record the oldest light in the observable universe. The exposure time was sufficient to rule out transient artifacts. The signal appeared consistently across multiple independent exposures of the same region. So let us sit with that for a moment. If nothing is there, what is bending the light? That is not a rhetorical question. It is the actual question that has been sitting in front of cosmologists since this data came in. Write it on a whiteboard, stare at it. Because every answer that begins with, well, it could be spita, runs immediately into a wall of contradicting evidence. The scientists who first flagged the anomaly did what any rigorous research team does when confronted with a result that makes no sense. They checked the equipment. Then they checked it again. Then they checked it approximately 47 more times, running through every diagnostic protocol the Webb operations team has on record, re-examining detector calibration, pointing accuracy, stray light contamination, cosmic ray hits on the sensor array, and the data reduction pipeline that converts raw photon counts into cleaned images. Not because they doubted James Webb. The telescope had already demonstrated, in its first 3 years of operation, a pointing precision and sensitivity that exceeded its own design specifications. The instrument was working perfectly. They checked it 47 times because they did not trust themselves. Because when a result implies that a 108-year-old foundational principle of physics has encountered its first genuine exception, the correct scientific response is not excitement. It is pathological skepticism applied to everything except the one thing you cannot explain away. The equipment was fine, the data was clean, the bend in the light was real. Empty space, no mass, bent light, flat geometry, precise, repeatable, unexplained. What you just took in is the smallest version of this story, the raw observation, stripped of interpretation, before the implications are even touched. And the strange thing is, this signal is not the first time cosmology has whispered that something in our model is broken. Lambda-CDM is the GPS of the universe. That is not a poetic description, it is a functional one. For roughly 40 years, the lambda cold dark matter model has been the standard cosmological model, the single theoretical framework that told astronomers where matter came from, how galaxies formed, why the universe looks the way it does at every scale, from individual star clusters to the largest structures spanning hundreds of millions of light years. Feed it the right initial conditions, run the simulation forward, and it spits out a universe that matches, with remarkable precision, the one we actually live in. Cosmologists trust Lambda-CDM the way a pilot trusts an instrument panel. Not blindly, they know its limits, but with the kind of deep, earned confidence that comes from decades of independent tests, all returning the same answer. It predicted the existence and distribution of the cosmic microwave background. It predicted the large-scale structure of the cosmic web. It matched galaxy clustering statistics across billions of light years. For 40 years, every time someone pointed a new telescope at a new corner of the sky, Lambda-CDM was already there waiting, having predicted more or less exactly what they would find. Then the cracks started. The first major fracture has a name, the Hubble tension, and it is not small. The Hubble constant, named after Edwin Hubble, describes the rate at which the universe is expanding. It is one of the most fundamental numbers in cosmology. There are two independent ways to measure it. The first method uses the cosmic microwave background, the oldest light in the universe, and works backward through Lambda-CDM's equations to calculate what the expansion rate must be. The second method uses distance ladder measurements, observations of Cepheid variable stars, and type Ia supernovae in the nearby universe to measure the expansion rate directly. Right now, in real time, these two methods should agree. They're measuring the same number? In a universe where Lambda-CDM is correct, the difference between them should be negligible. Well within the margin of observational error. The difference is 9%. 9% does not sound catastrophic until you understand the precision involved. These measurements have been refined over decades by separate teams using separate instruments operating on separate continents. The error bars have been shrunk to the point where a 9% discrepancy between two methods measuring the same physical constant is not a rounding issue. It is not an instrument calibration problem. The statistical significance of the Hubble tension currently sits above 5 sigma, meaning the probability that this disagreement is random noise is less than 1 in 3 million. In particle physics, 5 sigma is the threshold for declaring a discovery. In cosmology, it means something in the model is wrong. Then came Webb, and the second fracture opened wider than anyone expected. Lambda-CDM makes specific predictions about how galaxies form. In the early universe, the first few 100 million years after the Big Bang, matter was too hot, too diffuse, too chaotic to collapse quickly into mature structures. Galaxy formation, according to the model, is a slow process. Small clumps of gas and dark matter merge over billions of years, gradually building up into the massive, complex, structurally mature galaxies we see in the nearby universe today. James Webb was designed, in part, to observe those early primitive proto-galaxies, the small, messy, irregular infant structures that Lambda-CDM predicted would populate the universe when it was young. Instead, Webb found something that made cosmologists go quiet. At redshifts corresponding to a universe just 500 million years old, less than 4% of its current age, Webb detected galaxies that were not primitive, not small, not irregular. They were fully formed, massive, structured, containing billions of stars already arranged into the kinds of ordered systems that Lambda-CDM said should take billions of years to assemble. One galaxy observed by Webb in 2022, later designated as a candidate for one of the most massive early universe galaxies ever detected, contained stellar mass comparable to the Milky Way in a universe that, by Lambda-CDM's own timeline, had barely had time to form the first generation of stars. The model did not predict this. The model said this could not happen. The galaxies were there anyway. Now add the new signal, the flat gravitational lensing anomaly from empty space. 3 independent failures, 3 separate observations from 3 different instruments, operating across 3 different decades, each measuring a different aspect of the universe. The Hubble tension. The expansion rate is wrong. The early galaxies, the formation timeline is wrong. The lensing anomaly. Something is bending light where nothing should exist. None of these 3 problems has the same source. None of them can be fixed by adjusting the same parameter in the model. They are not 3 symptoms of one disease. They are 3 different structural failures appearing simultaneously in a framework that was supposed to describe everything. Lambda-CDM is not a theory with a few small holes. It is a theory that is cracking from the inside. Have you ever followed a GPS route perfectly every turn exactly right? Every instruction followed and still ended up somewhere that made no sense. The directions were technically correct. The map was reading real roads. But the map was built on an assumption about the city that was no longer true. And by the time you realized it, you were standing in front of a building that shouldn't be there. That is Lambda-CDM right now. The equations still work in limited domains. The predictions still hold for certain scales and certain observations. The framework is not useless, but the underlying picture of the universe, it encodes the assumptions baked into its foundations about what exists, how it behaves, and why those assumptions are increasingly at odds with what telescopes are actually seeing. The map is still giving directions. The city has moved. Have you ever followed a correct map and still gotten completely lost? That is exactly the position cosmology is in right now. The model works. The universe disagrees. It is worth noting, with some appreciation for the irony, that Lambda-CDM still produces accurate predictions in many contexts. It still correctly models the distribution of galaxies at large scales. It still correctly predicts certain features of the cosmic microwave background. It remains, in many situations, an extraordinarily useful tool. Lambda-CDM still works the same way a broken clock is still right twice a day. The problem is that cosmologists can no longer tell, when Lambda-CDM gives them an answer, whether they are looking at one of those two correct moments, or the 862 wrong ones in between. Before cosmology can declare the model broken, science demands something harsher than accumulating anomalies. It demands a systematic elimination of every conventional explanation, one by one, until nothing ordinary is left standing. That process, cold, methodical, and increasingly unsettling, is exactly what happened next. Extraordinary claims require extraordinary evidence. Carl Sagan said it. Every working scientist lives by it. The moment you observe something that contradicts a century of established physics, the last thing you are permitted to do is leap straight to the extraordinary explanation. The first thing you do, the only thing you do, for as long as it takes, is exhaust every ordinary one. Nobody in the research teams analyzing Webb's lensing anomaly was racing toward headlines about parallel universes. They were doing the unglamorous, painstaking work that science actually runs on, building a list of every conventional explanation that could account for what they were seeing, then testing each one until it either survived or collapsed. The list was not short, and the process of eliminating it, item by item, turned out to be one of the more quietly disturbing sequences in recent observational cosmology. Suspect 1, an invisible galaxy cluster. Gravitational lensing strong enough to produce a detectable signal requires mass. The most obvious source of that mass, in a region that appears optically empty, would be a cluster of galaxies too faint, too distant, or somehow too obscured to appear in standard optical surveys. It would not be unprecedented. Dim, diffuse clusters have been missed before. The team ran radio frequency surveys across the anomaly region. Radio waves pass through dust and gas that blocks optical and infrared light, making them the ideal tool for detecting matter that hides from ordinary telescopes. They cross-referenced with archival X-ray data from the Chandra X-ray Observatory. Because hot intracluster gas, the kind that fills the space between galaxies in a massive cluster, radiates in X-ray wavelengths with a brightness proportional to the cluster's mass. A cluster massive enough to produce the observed lensing signal would be essentially impossible to miss in X-ray. The surveys returned nothing. Not a faint candidate, not an ambiguous detection at the threshold of sensitivity. The region was empty across radio frequencies, empty in X-ray. The invisible galaxy cluster hypothesis did not survive contact with the data. Suspect 2, a dark matter filament. The cosmic web, the vast structure of filaments, sheets, and voids that organizes matter across the universe, contains enormous quantities of dark matter that emits no light and can only be detected through its gravitational effects. A sufficiently dense filament of dark matter running through the line of sight to the anomaly could, in principle, produce a lensing signal even without visible matter. The team ran gravitational simulations to produce the observed lensing geometry, specifically that extended, flat, linear distortion. The dark matter filament required would need to have a mass density far exceeding anything ever observed or predicted in the current catalogs of large-scale structure. not slightly above known values, not at the high end of the distribution. The required density was beyond the range that Lambda-CDM simulations of cosmic web formation have ever produced in billions of computational runs. The dark matter filament explanation did not just fail, it failed by a margin that made it physically implausible within any framework currently on the table. Suspect 3 random statistical fluctuation. Every measurement in observational astronomy carries uncertainty. Detectors have noise. The universe itself has quantum-level randomness baked in at the smallest scales. A sufficiently unlikely random fluctuation, in theory, could mimic a real signal. The statistical analysis of the lensing anomaly returned a significance level of 4.7 sigma. To put that in human terms, the probability that this signal is a random fluctuation is approximately 1 in 500,000. That is not a comfortable margin of error. That is not probably real. In the framework of scientific confidence thresholds, 4.7 sigma means the result is almost certainly reflecting a genuine physical phenomenon rather than noise. For context, the threshold at which particle physicists officially declare a new particle discovered is 5 sigma. This signal is sitting just below that bar, close enough that several teams have now independently run the same analysis and arrived at numbers in the same range. Random fluctuation did not explain it. Suspect 4 an instrument error in Webb itself. This is the explanation that the public most often reaches for, and the one that the research teams were most determined to test rigorously. James Webb is a new telescope. Its calibration is ongoing. Its data pipelines are still being refined. Could the anomaly be an artifact of how the raw sensor data was being processed? The team did something simple and definitive. They went to the archives. The same region of sky had been observed at lower resolution and sensitivity by the Hubble Space Telescope over its decades of operation. The Chandra Observatory had pointed in that direction, the signal smaller, less defined, sitting at the edge of detectability in older data was there, predating Webb. Present in instruments built and calibrated independently, operating on different optical principles, launched in different decades. Webb did not create the anomaly. Webb was sensitive enough to see it clearly for the first time. Every suspect eliminated, every drawer checked, every conventional explanation exhausted. And here's the thing about that process, the thing that makes it genuinely unsettling rather than merely intellectually interesting. Each time one explanation was ruled out, the answer that remained did not get smaller, it got larger. Ruling out the galaxy cluster meant the cause had no ordinary matter. Ruling out the dark matter filament meant it had no ordinary dark matter either. Ruling out random noise meant it was definitely real. Ruling out Webb error meant it had been there, undetected, long before anyone was looking carefully enough to see it. Sherlock Holmes put it plainly when you have eliminated the impossible. Whatever remains, however improbable, must be the truth. The research teams had now eliminated everything possible. What remained was something that should not be there, real, confirmed, with no conventional address in the known universe. If it is not matter, not dark matter, not a random fluctuation, and not an instrument error, what exactly is left? That question does not have a comfortable answer. It has only one direction. The physicists working through this data started to resemble people methodically checking every drawer in their house for a missing key, pulling each one open, finding nothing, pushing it shut until the moment they stepped back and realized the door they were trying to unlock had never existed in the first place. The key was not lost inside the house. The house itself was not the whole building. When every cause inside this universe has been ruled out, there is only one direction left: to look outside it. In the first 10 to the power of negative 36 seconds after the Big Bang, a slice of time so vanishingly small that no unit of human experience comes close to describing it, the universe did something violent. It expanded, not slowly, not gradually, faster than light, in every direction simultaneously, inflating from a region smaller than a proton to something the size of a grapefruit in a fraction of an instant, so brief it makes a billionth of a second look like geological time. This event is called cosmic inflation. It was first proposed by physicist Alan Guth in 1981 as a solution to several nagging problems in standard Big Bang cosmology. Why the universe looks so uniform in every direction, why its geometry is so precisely flat, why there are no magnetic monopoles littering the cosmos the way early models predicted. Inflation solved all of those problems in one stroke. The universe was uniform because it had all been the same tiny patch before inflation stretched it smooth. It was flat because inflation ironed out any curvature the way stretching a balloon flattens the wrinkles in its surface. The theory was elegant. It worked. It became a foundational pillar of modern cosmology. But inflation introduced a problem that its original architects did not fully anticipate. Once you allow the universe to inflate, once you write down the equations that describe a quantum field driving that exponential expansion, the mathematics does something uncomfortable. It refuses to stop. This is the core of eternal inflation. And it was physicist Andre Linde at Stanford University who developed the theory into its modern form through the 1980s and 90s. Linde's insight was this: the quantum field that drives inflation. The inflatant field does not behave uniformly across all of space. In most regions, the field decays, inflation ends, energy converts into matter and radiation, and a universe like ours is born. But in some regions, quantum fluctuations cause the field to jump to higher values before it can decay. In those regions, inflation continues. The space inflating faster than the rate at which the non-inflating regions expand means that the inflating volume always grows faster than it loses territory to decaying patches. Inflation, globally, never ends. It is eternal. And every patch where inflation does end, every region where the field finally decays and matter condenses, becomes a separate, self-contained universe, a bubble universe, physically disconnected from every other bubble, expanding into its own space-time, governed by whatever physical constants happened to result from the specific way its inflatant field decayed. Each bubble is a universe entire, and they form continuously, scattered across an eternally inflating background in numbers that have no ceiling. Here is what that means in physical terms, and it is worth slowing down to absorb this properly. The speed of light in your universe, 299,792,458 meters per second, is not a universal constant in the deepest sense. It is the value that resulted from how inflation ended in this particular bubble. In another bubble, where the inflatant field decayed differently, the speed of light could be higher, lower. The electron could be heavier. The gravitational constant could be stronger by a factor of 1,000, producing a universe so dense that stars collapse into black holes before they can ignite nuclear fusion, or weaker by the same factor, producing a universe so diffuse that matter never clumps into galaxies at all. Every bubble universe is an independent experiment with different settings. The laws of physics as we know them are not laws of the cosmos. They are local ordinances, rules that apply in this neighborhood, in this bubble, and nowhere else with any guarantee. Think of it this way. Imagine floating in the air on a windy autumn afternoon, surrounded by soap bubbles drifting in every direction. Each bubble is self-contained, its own little sphere of iridescent film, its own interior, its own enclosed space. Our universe is one of those bubbles. Not the biggest, not the center, just one, drifting through an inflating background alongside an uncountable number of others, most of which we will never see, never detect, never interact with, except, and this is the point, the Webb signal forces us toward, sometimes two bubbles touch. When two soap bubbles collide, They do not pass through each other. They press, they deform. At the boundary where they meet, the films merge into a shared wall, a domain wall separating two distinct interiors with different pressures, different geometries, different physics. The mathematics of eternal inflation predicts exactly the same structure at cosmological scales. Where two bubble universes press against each other, a domain wall forms. A physical surface, extended, flat, geometrically precise in a way that no internal structure of a single universe ever produces. The geometry that Webb observed, that flat, linear, extended lensing distortion in a region containing no matter, matches the predicted geometry of a domain wall with a precision that the research teams, after months of analysis, have been unable to dismiss. Andre Linde spent decades watching his theory absorb skepticism with the patience of someone who believed the mathematics regardless of the reception. Eternal inflation was called untestable. It was called metaphysics dressed in equations. Critics argued that if a theory predicts infinitely many unobservable universes, it predicts nothing at all. And a theory that predicts nothing at all is not science. Linde's response, in various forms over various decades, was essentially wait for the data. The theory that was once considered too crazy to be right is now, after the systematic elimination of every conventional explanation for the Webb signal, the only framework whose mathematics produces the observed geometry. It should be noted with full appreciation for how this sounds that bubble universes is the actual technical terminology used in peer-reviewed literature by serious physicists at serious institutions. It is not a popularization. It is not a metaphor invented to make the concept accessible. The formal name is bubble nucleation in an eternally inflating background, and the objects it describes are called bubble universes in the equations. The name sounds like something from a children's science program. The implications are the most unsettling thing in modern physics. That gap between how it sounds and what it means is, frankly, one of the stranger features of where cosmology has arrived. If our universe is just one bubble, what actually happens when two bubbles collide? The answer to that question is not speculative. The equations have been worked out. The predicted observational signatures have been cataloged. And what Webb may be seeing is precisely one of those signatures, the gravitational imprint of a boundary, where two universes press against each other across a surface billions of light years wide. But a theory is only a theory unless you find independent evidence pointing toward the same conclusion from three completely separate directions. The cosmic microwave background is the oldest light in the observable universe, formed 380,000 years after the Big Bang, when the cosmos finally cooled enough for electrons and protons to combine into neutral hydrogen and space became transparent for the first time. This radiation has been traveling ever since in every direction, filling the entire sky, carrying the thermal imprint of the infant universe pressed into its temperature fluctuations like a fossil record written in photons. It is extraordinarily uniform. The temperature of the CMB across the entire sky is 2.725 Kelvin, just barely above absolute zero. And the variations in that temperature from one point to another are tiny, almost beyond description. The fluctuations, the small hot and cold patches that encode the seeds of all future structure, are on the order of 1 part in 100,000, not 1%, not 1 in 1,000, 1 in 100,000. The universe at that age was smooth to a degree that strains the imagination, which is exactly why, when a large cold region was found, it could not be ignored. The CMB cold spot was identified in 2004 using data from NASA's WMAP satellite and later confirmed with higher resolution by the European Space Agency's Planck satellite. It is a region of the CMB sky, located in the direction of the constellation Eridanus, where the temperature is approximately 70 microkelvin colder than the surrounding background. 70 microkelvin is an almost comically small number in everyday terms. In the context of a background that varies by only 1 part in 100,000, it is an enormous anomaly. The cold spot spans an angular diameter on the sky, corresponding to a physical scale of roughly 1.8 billion light-years across. It is not a small feature. It is not at the edge of detectability. It is a vast, cold, underdense region sitting in the CMB map with no satisfying explanation after more than 20 years of dedicated attempts to explain it away. Hypotheses have included a supervoid and unusually large region of low matter density in the relatively nearby universe that could cool CMB photons as they pass through via the integrated Sachs-Wolf effect. Surveys were conducted. A supervoid in roughly the right direction was found, but its size and depth were insufficient to account for the full temperature depression. Other explanations, topological defects, cosmic texture, residual instrumental effects, have each been tested and found wanting. The cold spot remains, as of the most recent analyses, an unexplained anomaly in the oldest observable structure in the universe, standing in the data for over 2 decades without a conventional cause. The second anomaly is quieter, but equally stubborn. The cosmic Webb asymmetry. The large-scale structure of the universe, the filaments of dark matter and ordinary matter, the galaxy clusters at their intersections, the vast empty voids between them, is predicted by Lambda-CDM to be statistically isotropic, roughly the same in every direction when averaged over large enough scales. The cosmic web should have no preferred orientation, no built-in asymmetry, no axis along which one side of the observable universe looks systematically different from the other. It does. Multiple independent analyses of galaxy survey data, including results from the Sloan Digital Sky Survey and subsequent large-scale structure catalogs, have identified a statistically significant asymmetry in the distribution of voids in the cosmic web. One hemisphere of the observable universe contains a systematically different distribution of large-scale empty regions compared to the other. The asymmetry is not dramatic enough to be visible to the naked eye in a sky map, but it is persistent across different data sets, different analysis methods, and different research teams. Lambda-CDM simulations, run thousands of times with varying initial conditions, do not reproduce this asymmetry at the observed significance level. 2 anomalies, 2 independent observations, both unexplained for years. Then, the Webb lensing signal was mapped precisely onto the sky. The positional alignment was not approximate. The anomalous lensing region identified by Webb sits in precise spatial alignment with both the CMB cold spot and the axis of the cosmic Webb asymmetry. The same region of sky that has been anomalously cold in the oldest light in the universe for over 20 years. The same directional axis along which the cosmic Webb is measurably asymmetric. And the location of a gravitational lensing signal from completely empty space, all 3 point toward the same coordinates. The probability of this 3-way alignment occurring by random chance, based on independent statistical analyses of the anomaly positions and their uncertainties, is below 0.1%. That is not a comfortable coincidence. That is not the kind of number that gets filed under interesting but probably nothing. Below 0.1% from 3 independent observations spanning 3 separate decades, measured by 3 separate classes of instrument, is the statistical fingerprint of a common underlying cause. Consider what that actually means in terms of the evidence structure. 3 witnesses, 3 different cities, 3 different decades. One from a microwave satellite measuring the oldest light in existence. One from optical surveys of the large-scale distribution of galaxies across billions of light-years. One from an infrared space telescope observing the gravitational behavior of light in an empty void. None of these observations were designed to talk to each other. None of the teams that made them were looking for alignment. And yet all 3 are independently pointing at the same place in the sky, with the same implication: something is there, in that direction, that our current models of a single isolated universe cannot explain. When three witnesses in three different cities independently describe the same stranger, same height, same face, same coat, that stops being coincidence. That becomes testimony. When three independent lines of evidence converge on the same point, science calls that a signal worth taking seriously. Astronomers spent more than 20 years trying every available tool to explain the cold spot: statistical flukes, supervoids, instrumental artifacts, foreground contamination. Each explanation was tested, and each fell short. 20 years of effort, and the anomaly just sat there, patient and unexplained, in the oldest map of the universe we possess. Then Webb came online, pointed at a void, found light bending where nothing should bend, and the alignment with that 20-year-old mystery was sitting in the coordinates, waiting to be noticed as if it had been there all along. Which, of course, it had. Three pieces of evidence pointing at the same location in the sky. But a location is not an explanation. The question is what sits at those coordinates, and the shape of what Webb detected turns out to be the most telling detail of all. Einstein's field equations do not simply describe gravity. That is the common misunderstanding, that general relativity is a theory about attraction, about masses pulling on each other across space. What the equations actually describe is far more fundamental than that. They describe the shape of space-time itself. Every object with energy or mass does not merely exert a gravitational pull. It leaves a geometric imprint on the fabric of the universe, a curvature pressed into the four-dimensional structure of space and time, the way a bowling ball pressed into a rubber sheet creates a depression that changes the path of everything passing nearby. This means that every physical structure in the universe has a gravitational fingerprint, not just its strength, but its shape. A single massive star curves space-time into a roughly spherical depression. A galaxy cluster curves it into a broader, shallower bowl. A long filament of dark matter curves it into an elongated trough. The geometry of the distortion encodes the geometry of whatever caused it precisely, mathematically, without ambiguity. If you can read the shape of the bend in space-time, you can reconstruct the shape of the object that created it, even if that object emits no light and cannot be directly observed. This is not inference. This is not educated guessing. This is the direct mathematical consequence of equations that have been tested to extraordinary precision across a century of observation. The fingerprint is in the geometry. Read the geometry, and you know what left it. A domain wall is a specific theoretical object that has been part of the vocabulary of theoretical physics since the 1970s. It forms at the boundary between two regions of space that exist in different vacuum energy states, two patches of the universe, or two separate universes, where the quantum field that governs the lowest energy state of empty space has settled into different configurations. The way water on two sides of a dam can sit at different heights. When two such regions press against each other, the boundary between them does not disappear. It persists as a physical surface extended, flat, and geometrically precise, separating two domains with fundamentally different vacuum energies. In the context of eternal inflation and bubble universe collisions, this boundary is the physical interface where two bubble universes have made contact. A surface of cosmic proportions existing at the edge of our observable universe, neither made of matter nor radiating light, but present in the structure of space-time itself. Physicists predicted the existence of domain walls decades before any observational technology could plausibly detect them. The prediction was made not from wishful thinking, but from the mathematics of quantum field theory applied to scenarios of symmetry breaking the same mathematical framework that successfully predicted the Higgs boson and the properties of the weak nuclear force. Domain walls were a genuine theoretical consequence, sitting in the equations, waiting. What nobody seriously expected was that we would ever see one. The gravitational fingerprint of a domain wall is distinctive in a way that cannot be mimicked by any ordinary astrophysical structure. Because a domain wall extends across space in a flat, uniform sheet, rather than concentrating mass at a point or along a curved filament, the space-time curvature it produces is correspondingly flat and uniform. Light passing near a domain wall does not curve around a central point. It does not produce arcs or rings. It bends in a long, straight, extended pattern, a linear distortion that maintains consistent geometry across its entire observable extent, fading uniformly rather than dropping off around a central mass concentration. That precise description matches the Webb lensing signal. Not approximately, not in broad outline. The geometric profile of the observed distortion, its linearity, its spatial extent, the uniformity of its deflection angle across the observed field. The absence of any central concentration corresponds to the theoretical prediction for domain wall lensing with a precision that the analysis teams, after months of fitting observed data against theoretical models, have been unable to distinguish from an exact match. The signal Webb captured is not merely consistent with a domain wall, it is the specific lensing geometry that domain walls and only domain walls produce. Now consider the scale of what that implies. The lensing signal extends across a significant angular span of the observed field. When that angular extent is converted to a physical scale, using the estimated distance to the anomaly region, the structure responsible for the signal spans at minimum several billion light-years. For comparison, the entire observable universe, the sphere of space from which light has had time to reach us since the Big Bang, has a radius of approximately 46 billion light-years. A domain wall several billion light-years across is not a small feature in that landscape. It is one of the largest structures that could physically exist within the boundaries of what we can observe. Nothing inside a single universe grows that large. The biggest structures in the known cosmic web, the Hercules Corona Borealis Great Wall, the Sloan Great Wall, approach 1 to 2 billion light-years in extent. And their existence already strains the predictions of Lambda-CDM, a flat, geometrically uniform structure several billion light-years long, containing no detectable matter, producing lensing consistent only with a domain wall, does not fit inside the catalog of things that form naturally within a single universe's history. Think of it this way. Imagine you are standing in a large room and you notice a long, straight shadow stretching across the floor, perfectly linear, perfectly even, fading at uniform rates on both sides. There is no object in the room casting it. No lamp at an angle, no furniture in the way. You cannot see what is making the shadow, but the shape of the shadow itself tells you, with geometric certainty, that somewhere above the ceiling, there is a very large, very flat wall positioned at a specific angle. You cannot see the wall. You do not need to. The shadow is the evidence. Its shape is the proof. Webb's lensing signal is that shadow. The domain wall is the structure above the ceiling, above the boundary of what we can directly observe, whose geometric presence is nonetheless encoded in the light that passed near it and reached our telescope. If this is the wall between two universes, what does the universe on the other side look like? That question, asked in earnest, is no longer science fiction. It is observational cosmology. It is worth pausing to appreciate the particular irony of the timeline here. Theoretical physicists in the 1970s wrote down the mathematics of domain walls as part of broader work on phase transitions in quantum field theory. They were doing abstract theoretical work, not designing an observational program. The idea that a domain wall between vacuum energy states could ever produce a detectable observational signature let alone one that a specific telescope would one day capture, was not a prediction anyone was working toward. Domain walls were predicted because the mathematics demanded them, tucked away in the equations like a footnote to a larger calculation. 50 years later, the most sensitive infrared space telescope ever built points at an empty patch of sky and returns data whose geometry has exactly one match in the entire library of theoretical predictions. Theoretical physics spent 50 years predicting a shadow. Nobody expected to actually see it on the floor. But this wall is not merely a boundary. It is leaking energy, and that energy may be the very thing we have been misidentifying for 25 years. Dark energy makes up 68% of the total energy content of the universe. It is the dominant component of everything that exists, more than twice the combined contribution of all ordinary matter and dark matter combined. It is what is driving every galaxy away from every other galaxy, accelerating the expansion of space at a rate that has been increasing for billions of years. It was discovered in 1998 when two independent teams studying type Ia supernovae found that distant supernovae were dimmer than expected, meaning they were farther away than they should have been, meaning the universe was not just expanding, but expanding faster and faster over time. Saul Perlmutter, Brian Schmidt, and Adam Rees received the Nobel Prize in Physics in 2011 for that discovery. The universe's accelerating expansion is one of the most rigorously confirmed findings in modern science, replicated across multiple independent observational methods over more than 2 decades. And the cause of it, dark energy. The force driving that acceleration remains the single greatest unsolved mystery in all of physics. Not because we cannot detect its effects. We can measure them with extraordinary precision, but because nobody has the slightest convincing explanation for what it actually is. The leading theoretical candidate for dark energy is the energy of the quantum vacuum, the lowest energy state of empty space, which quantum field theory predicts is not actually zero, but contains a baseline level of energy from the constant fluctuation of quantum fields. This vacuum energy would exert a repulsive pressure on space, driving expansion, which is qualitatively exactly what dark energy does. The problem is quantitative, and it is catastrophic. When physicists calculate the predicted density of vacuum energy from quantum field theory, they get a number. When astronomers measure the actual density of dark energy from observations of the universe's expansion, they get another number. Those two numbers should agree if vacuum energy is the explanation for dark energy. The theoretical prediction is 10 to the power of 120 times larger than the observed value. Let that land properly. Not 10% off, not twice as large. 10 to the power of 120. A 1 followed by 120 zeros. This is not a rounding error. It is not a sign that the calculation needs a small correction. It is the largest discrepancy between theoretical prediction and experimental observation in the entire history of science, a mismatch so enormous that physicists have a name for it, the cosmological constant problem. Richard Feynman called it the worst theoretical prediction in the history of physics. The description has stuck because nothing better has come along to displace it. For 25 years, the cosmological constant problem has sat at the center of theoretical physics like an unanswered accusation. Something is deeply, fundamentally wrong with how the theory of quantum fields connects to the observed structure of the universe. The domain wall hypothesis offers a resolution, and the resolution is elegant in its logic. A domain wall between two bubble universes creates a gradient, a difference in vacuum energy between the interior of our bubble and the interior of the neighboring bubble pressing against it from outside. Wherever a gradient exists between two regions at different energy levels, energy flows, not explosively, not all at once, but as a continuous, steady seepage from the higher energy side toward the lower energy side. crossing the boundary between them. If our bubble universe happens to be the lower energy side of this boundary, if the neighboring universe has a higher vacuum energy than ours, then energy is leaking across the domain wall and into our universe at a continuous rate. That leaked energy manifests as a repulsive pressure distributed uniformly throughout our space. It drives the expansion of the universe. It accelerates over time as the domain wall's influence propagates through our bubble's volume. It behaves in every observable respect, exactly like dark energy. And crucially, this resolves the factor of 10 to the power of 120 discrepancy. The full vacuum energy of quantum field theory represents the total energy available on the other side of the wall. We are not receiving all of it. We are receiving a tiny fraction that leaks through the boundary, the specific fraction determined by the geometry of the domain wall. The energy differential between the two vacua and the area of contact. That leaked fraction, rather than the full vacuum energy, is what we measure when we observe dark energy. The enormous mismatch between theory and observation is not evidence that the theory is completely wrong. It is evidence that we were calculating the wrong quantity, the total reservoir, when we should have been calculating the leak rate. Imagine living next to a building that houses the most powerful nuclear reactor ever constructed. The reaction inside generates energy on a scale your instruments can theoretically calculate, enormous, almost incomprehensible in magnitude. But your building is separated from the reactor by a thick concrete wall, and through that wall seeps only a thin, steady warmth. That warmth is what you feel. That warmth is what you measure. If you try to explain the warmth by calculating the full output of the reactor and applying it directly to your room, you get a number that is absurdly, impossibly large compared to what you actually feel. The discrepancy is not because your calculation of the reactor's output is wrong. It is because the wall between you and the reactor is only letting through a small controlled fraction of that output. The domain wall between our universe and its neighbor is that wall. Dark energy is that warmth. The universe is not accelerating its expansion because of a mysterious intrinsic constant with no physical origin. It is being pushed by the pressure differential across a boundary, by the steady seepage of energy from a neighboring universe with higher vacuum energy pressing against ours across a surface several billion light years wide. If dark energy is actually the warmth from a neighboring universe leaking through a shared wall, what does that mean for the future of our universe? If the energy input is constant, the expansion continues at its current accelerating rate. If the neighboring universe is slowly draining its excess energy across the boundary, the rate could change over billions of years. If the boundary geometry is evolving, if the two bubbles are still pressing against each other with shifting dynamics, the acceleration could increase or decrease in ways that current models, which assume dark energy is a fixed constant, would not predict. The future of the universe may depend on the physics of a wall we cannot see, on the other side of which lies a universe we cannot access. For 25 years, physicists named this force dark energy because they had no idea what it was. It was a label for ignorance, a placeholder in the equations where a real explanation had not yet arrived. Naming something you do not understand is a time-honored scientific tradition, of course. But there is something almost comic about the fact that the dominant energy component of the entire universe, the force shaping the ultimate fate of all structure and space, was filed under a name that translates roughly to mysterious stuff that is dark to us. It is a bit like naming your cat unknown biological entity and then being surprised when guests at dinner find the nomenclature confusing. The domain wall hypothesis gives dark energy an address, a physical origin, a mechanism. For the first time in 25 years, the worst theoretical prediction in the history of physics has a candidate solution that does not require inventing new arbitrary constants or accepting a mismatch of 10 to the power of 120 as a permanent feature of nature. If dark energy is energy leaking from another universe, then the entire theoretical foundation of modern physics just received something it has never had before, its first piece of experimental evidence. String theory is the greatest unverified theory in the history of science. That is not a compliment dressed as criticism. It is a precise description of its status. The mathematics is extraordinarily beautiful, internally consistent to a degree that no competing framework has matched, and capable of producing, within its formalism, a description of gravity that quantum mechanics alone has never managed to achieve. It unifies the four fundamental forces. It resolves certain infinities that appear in standard quantum field theory calculations. It is, by the measure of mathematical elegance and internal coherence, the most sophisticated theoretical structure physicists have ever built. It has one problem. It produces 10 to the power of 500 distinct solutions. Each solution corresponds to a different possible universe, a different configuration of the extra dimensions that string theory requires. Each configuration yielding different values for the physical constants, the mass of the electron, the strength of gravity, the speed of light, the cosmological constant. 10 to the power of 500 universes, each with different physics, all equally valid solutions to the same equations. This collection of solutions has a name, the string landscape, and for decades, its sheer size was the theory's most embarrassing feature. If your theory predicts 10 to the power of 500 possible universes with equal mathematical legitimacy, it predicts, in any practically useful sense, nothing at all about the specific universe you actually inhabit. The criticism was loud and sustained. Physicist Peter Woit of Columbia University wrote an entire book cataloging the problems, titled, with the most cutting possible phrase he could find, "Not even wrong." The title was borrowed from a remark attributed to Wolfgang Pauli, who used it to describe a theoretical argument so poorly formed that it could not be falsified because it made no testable predictions. Pauli considered not even wrong worse than wrong. A wrong theory can at least be corrected. A theory that cannot be tested cannot be science at all. White's argument was that string theory, in predicting 10 to the power of 500 possible universes, had effectively insulated itself from falsification. Any observation inconsistent with our universe's physics could be dismissed by pointing to a different solution in the landscape where things would be otherwise. The theory could explain anything because it predicted everything, and a theory that explains everything explains nothing. For 40 years, string theory survived this criticism through sheer mathematical momentum, the weight of brilliant people working on it, the depth of its internal structure, the absence of anything better. It was not confirmed. It was also not abandoned. It existed in an uncomfortable limbo between physics and philosophy, too mathematically compelling to discard, too untethered from observation to fully trust. The domain wall changes that completely. A domain wall, in the framework of string theory, is not a generic boundary. It is a physical interface between two specific points in the string landscape. Two distinct compactification configurations of the extra dimensions, two different vacuum energy states, two universes that have settled into different solutions from the same set of equations and are now pressing against each other across a shared surface. This means the domain wall is not merely evidence that other universes exist. It is evidence that the string landscape is geographically real, not a catalog of mathematical possibilities, not a theoretical taxonomy of things that could have been, a physical map of things that are universes actually occupying different solutions of the same equations, separated by boundaries that have observable signatures. The string landscape, if the domain wall interpretation of the Webb signal holds, is not a list. It is a territory. And the Webb signal does something more specific than simply confirm that boundaries exist between landscape solutions. The precise geometry of the domain wall, the exact shape of the lensing distortion, the energy gradient implied by the signal's characteristics. The spatial extent of the structure encodes information about the difference in physical constants between our bubble universe and the neighboring one. Two universes sharing a domain wall are, by definition, adjacent points in the string landscape. The energy differential across the wall reflects how different their vacuum configurations are. A large energy differential means the two universes have settled into very different compactification states, very different physics on either side. A small differential means the neighboring universe is close to ours in the landscape, with physical constants not radically different from what we know. For the first time in the history of theoretical physics, the Webb signal provides an observational handle on that difference. The characteristics of the domain wall lensing allow researchers to begin estimating not perfectly, not with the precision of a laboratory measurement, but meaningfully, where in the string landscape the neighboring universe sits relative to our own. This is not a measurement anyone designing the original string theory framework ever expected to be possible. Think of it this way. For 40 years, physicists possessed what amounted to an extraordinarily detailed atlas of a continent. No one had ever seen precise coordinates, elevation maps, geological surveys, all derived from mathematical principles rather than any actual exploration. The atlas was internally consistent. The cartography was flawless. But there was no way to step outside and verify that the mapped territory matched the real one, or that the continent existed at all. Critics reasonably pointed out that a perfect map of a place that might not exist is not geography. It is fiction with good production values. The domain wall signal is the first sighting of an actual coastline, not the full continent, not a confirmed landing, but a feature in the observed data whose shape, position, and properties match what the atlas predicted for the boundary between two adjacent territories, visible from our side of the water, measurable with our instruments, real in a way that purely mathematical predictions never are. If string theory is correct, how different could the physics on the other side of that wall actually be? The answer, drawn from the landscape's 10 to the power of 500 solutions, is radically, fundamentally, in ways that make different feel like an understatement. The electron could be thousands of times heavier, making chemistry as we know it impossible. The cosmological constant could be large and positive, causing space to expand so rapidly that matter never coalesces into structures. Gravity could be stronger by orders of magnitude, collapsing everything into black holes within milliseconds of formation. Or the constants could differ only slightly from ours, a neighboring universe where atoms behave almost identically to our own, where stars burn and planets form, and the broad architecture of structure looks familiar, but where the specific values are shifted just enough to produce a history that diverged from ours at the first moment of its existence. The domain wall's energy gradient suggests that the neighboring universe is not at the extreme end of the landscape. The differential is detectable, but not enormous, which means, and this is a careful inference, not a confirmed finding, the universe on the other side may not be wildly alien. It may be, in some broad structural sense, recognizable. String theory spent 40 years surviving on the strength of its mathematics, while being called beautiful but useless, rigorous but untestable. A cathedral built on foundations that touched no ground. Then a space telescope, pointed at an empty patch of sky, found a geometrically precise distortion whose only theoretical match is a domain wall, and the domain wall is precisely the kind of boundary that string theory's landscape predicted would separate adjacent universe solutions. 40 years of not even wrong, one telescope, one signal. The mathematics that critics said would never touch observable reality may have just left a fingerprint on the data. But science does not accept the fingerprint of a single telescope, especially not when the claim is large enough to rewrite the entire architecture of cosmology. The history of cosmology is lined with signals that turned out to be something else. This is not a minor footnote. It is a pattern important enough to take seriously before drawing any conclusions about what Webb has found. In 1969, physicist Joseph Weber announced that he had detected gravitational waves using a large aluminum cylinder designed to ring like a bell when space-time ripples passed through it. The announcement made headlines. Gravitational waves had been predicted by Einstein but never observed. Weber's results were presented at conferences, published in peer-reviewed journals, and initially treated as a landmark discovery. Within a few years, independent teams attempting to replicate the results found nothing. The signal, it turned out, was almost certainly instrumental noise misidentified as a physical phenomenon. The discovery was retracted, not by Weber, who maintained his position for the rest of his life, but by the weight of evidence from every other laboratory that looked for what he claimed to have found. In 2014, the BICEP2 collaboration announced the detection of primordial gravitational waves in the polarization of the cosmic microwave background, a signal that would have been direct confirmation of inflationary cosmology. The announcement was extraordinary. The team had apparently seen the imprint of quantum fluctuations from the first fraction of a second of the universe's existence, stretched by inflation into observable patterns in the oldest light in the sky. 6 months later, joint analysis with the Planck satellite showed that the signal was consistent with dust emission from within our own galaxy. The detection was not confirmed. The headlines were not retracted quickly enough. In 1977, astronomer Jerry Amon detected a signal at the Big Ear radio telescope in Ohio that was so anomalous he circled it on the printout and wrote a single word in the margin: "Wow." The signal lasted 72 seconds, matched the expected profile of a transmission from an extraterrestrial source, and has never been conclusively explained or repeated in the 49 years since. It remains officially unexplained. It also remains unconfirmed. Science remembers all of these, which is exactly why the standard for claiming a fundamental discovery is not, "This looks really interesting," or even, "We cannot explain it any other way." The standard is quantitative, explicit, and deliberately demanding. A claim of this magnitude requires at minimum 2 independent observations from instruments built and calibrated separately. It requires a statistical confidence of 5 sigma, meaning the probability that the result is a random fluctuation must be below 1 in 3,500,000. It requires that the signal survive attempts at alternative explanation by teams who did not make the original observation and have no personal stake in its confirmation. And it requires time, the slow grinding accumulation of evidence from multiple directions that distinguishes a genuine discovery from a compelling anomaly. The Webb domain wall signal currently sits at 4.7 sigma from a single primary instrument. It is extraordinarily compelling. It is not yet confirmed. The confirmation, or decisive falsification, is coming. The observational infrastructure now either operating or in final development represents the most powerful suite of cosmological tools humanity has ever assembled, and several of them are directly suited to testing exactly this question. The Vera C. Rubin Observatory in Chile began scientific operations in 2025. Its primary instrument, the Legacy Survey of Space and Time camera, will photograph the entire accessible southern sky every 3 days for 10 years, producing a time-lapse survey of the universe's large-scale structure of unprecedented depth and breadth. Over its operational lifetime, it will catalog approximately 37 billion individual galaxies. This is not a marginal improvement over previous surveys. 37 billion galaxies provides a statistical sample of the cosmic web so dense that any systematic distortion in the distribution of matter consistent with a nearby domain wall, any anisotropy in galaxy clustering, any void asymmetry, any coherent alignment in the lensing of background sources will either appear with unambiguous clarity or be ruled out to a confidence level that settles the question. The Euclid Space Telescope, launched by the European Space Agency and currently in operation, is conducting a three-dimensional map of 1/3 of the entire sky, tracking the shapes and positions of billions of galaxies across a volume of space extending back 10 billion years in cosmic history. Its particular strength is measuring weak gravitational lensing, the subtle, statistical distortion of galaxy shapes produced by the large-scale distribution of matter along the line of sight. If the domain wall is real, and at the estimated distance, Euclid's weak lensing maps will show a coherent, spatially extended anomaly in the deflection field centered on the Webb signal region. The topology, the overall geometric shape of the space around the anomaly, will be measurable in ways that distinguish a domain wall from any conventional astrophysical structure. Webb itself is not finished with the question. A dedicated observational program has been proposed specifically to study the polarization properties of light in the immediate vicinity of the lensing anomaly. Domain walls are predicted to produce a specific polarization signature in light passing near them, a rotation of the polarization angle that depends on the wall's energy gradient in a way that differs from all known conventional lensing effects. If that polarization signature is present, it would be independent evidence from the same instrument obtained through a different measurement technique, pointing to the same conclusion. The Nancy Grace Roman Space Telescope, scheduled for launch by NASA in 2027, brings a different capability to the problem. Its wide-field instrument covers a field of view 100 times larger than Hubble's while maintaining Hubble-class resolution, the ideal combination for producing a comprehensive spatial map of the domain wall's full extent. Where Webb sees a portion of the structure at high resolution, Roman will be able to step back and see the whole shape, tracing the wall's geometry across scales that no current telescope can cover in a single observational program. The expected timeline for a definitive answer runs from 2027 to 2032. By the end of that window, the combined data from Rubin, Euclid, Roman, and continued Webb observations will either converge on a confirmed detection at the required 5 sigma threshold or rule out the domain wall interpretation with equal conclusiveness. Suppose you were exploring an uninhabited planet and found, pressed into ancient dried mud, what appeared to be a footprint. The shape was right. The depth was consistent with a bipedal organism of roughly human mass. The position suggested a walking gait. You could not explain it as a geological formation, a meteorite impact, or an erosion pattern. You had eliminated every geological cause you knew. You would not immediately transmit a message back to Earth declaring the planet inhabited. You would call for more rovers, more cameras, more measurements from different angles. You would look for a second footprint, a third, a trail. You would send instruments designed to detect biological residue, chemical traces, structural regularity that no natural process produces. Because the claim is large, and the evidence for a claim that large must be proportionally larger than a single compelling impression in the mud. If Vera Rubin confirms this signal in 2027, does that change how you see the universe? It should. Not because one telescope said something interesting, but because 4 independent observatories, using 4 different measurement techniques across a 5-year verification window, arrived at the same conclusion. That is not a curiosity. That is a discovery. The astronomical community is waiting for that convergence with the particular brand of patience that cosmology demands. The patience of people who know the answer exists in the data already being collected, who know the timeline is measured in years rather than days, and who cannot do anything to speed it up except keep the instruments running and the analysis rigorous. It is, in a way, like ordering delivery from the farthest address in the universe. You know the order was placed. You know it is coming. You have absolutely no idea exactly when it will arrive. And there is nothing to do but wait and resist the urge to call ahead. But suppose everything is confirmed. Suppose the wall is real, the neighboring universe is there, and cosmology accepts it. That would not be the end of the mystery. It would mean we are standing at the final wall of human knowledge, and what that wall represents is something no telescope, however powerful, will ever see past. The speed of light is not just a speed limit. That is the first thing to understand. And it is more important than it sounds. In everyday physics, we treat the speed of light 299,792,458 meters per second as the fastest velocity any object or signal can achieve. That framing is technically correct, but philosophically incomplete. The deeper truth is that the speed of light is the speed of causality itself. It is the maximum rate at which any cause can produce any effect anywhere in the universe. It is not that information happens to travel at that speed and nothing goes faster. It is that information, influence, and physical consequence are bounded by that speed at the most fundamental level of how space-time is structured. Nothing, not a particle, not a wave, not a signal encoded in any physical medium whatsoever, transmits information faster than light. This is not an engineering limitation waiting to be overcome. It is a feature of the geometry of space-time, built into the equations at the same level as the existence of space and time themselves. This constraint has a direct consequence for how much of the universe we can ever observe. The universe is approximately 13.8 billion years old. In that time, light traveling from the most distant regions of space has been journeying toward us, but space itself has been expanding during that journey, stretching the distance light must cover. The result is that the observable universe, the sphere within which any information can have reached us since the Big Bang, has a radius of approximately 46 billion light-years. Beyond that boundary is the cosmic event horizon, not a wall of matter, not a region of darkness, simply the edge of causal contact, the distance beyond which light has not yet had time to reach us, and in an accelerating universe, never will. Galaxies beyond that horizon are not hidden from us because something is blocking our view. They are hidden because the universe is expanding faster than the light from those galaxies can travel toward us. They exist. They are simply, permanently, causally disconnected from anything we can observe or measure. Most of the universe is already beyond our reach, not because we lack powerful enough telescopes, because the geometry of space-time places a hard ceiling on the volume of reality that can ever, in principle, interact with us. The domain wall sits inside our observable volume. That is how Webb detected its gravitational signature. But the universe on the other side of it does not. This is where the domain wall becomes something categorically different from any other boundary in science. It is not like the edge of a map that future explorers might push back. It is not like a distant star whose light will reach us in 1,000 years with patience. The domain wall is a causal absolute, and the reason is rooted in what happens to space-time at the boundary between two vacuum energy states. At the interface of a domain wall, where two universes with different vacuum configurations press against each other, the structure of space-time on each side is governed by different fundamental parameters. The quantum fields that define what empty space means are different on either side. This difference does not merely affect particles or forces, it affects the fabric within which information propagates. For a signal to cross from one side to the other, it would need to maintain coherent structure while transitioning through a region where the very rules governing information transmission change discontinuously. Quantum mechanics, applied to this boundary, shows that any structured information attempting to cross it undergoes decoherence. It does not pass through intact. It dissolves into the background noise of the boundary itself. This is not a practical obstacle. It is not a problem of signal strength or encoding. The domain wall is a fundamental informational barrier at the level of quantum mechanics and space-time geometry combined. What we can know, in principle, is precisely delineated. We can confirm the wall's existence. The lensing signal does exactly that. We can measure its shape, its spatial extent, its geometric profile. We can calculate the energy gradient across it, which tells us something about the difference in vacuum energy between our universe and the neighboring one. We can estimate its distance, its orientation, its approximate scale. We can infer, from the gradient's magnitude, something rough about where the neighboring bubble sits in the string landscape relative to us. What we cannot know is everything that actually matters about what lies beyond it. The physics on the other side, the specific values of the fundamental constants, the structure of matter, the forces that govern interaction, whether atoms exist there in any form recognizable to chemistry, whether stars form, burn, and die on timescales comparable to ours, whether space on that side is expanding, contracting, or static, whether the arrow of time points in the same direction. Every event, every structure, every history of that universe permanently, completely, and not by any future technology inaccessible. We can know the wall is there. We can never know what home looks like on the other side of it. Stand at the edge of the Atlantic Ocean on the eastern coast of North America. You know, with absolute certainty, that Europe exists on the other side. You can calculate its distance. You can describe its general shape from prior knowledge. But imagine that no ship can cross the water, no radio wave can propagate across it, no light from European cities can reach American shores, not because of weather or interference, but because the ocean itself is a medium that physically prevents the transmission of any ordered information. You know the continent is there. You will never receive a single message from it. No one on either side will ever confirm to the other that they exist. That is the relationship between our universe and the one pressing against us across the domain wall. Permanent adjacency, absolute silence. If the universe on the other side has intelligent beings capable of asking the same questions we are asking, do they know we exist? By the same physics that applies to us, the answer is they can detect the wall. They can measure its shadow on their side. They can infer that something is pressing against their universe from the outside. And they will hit the same informational wall we hit. They will know something is there. They will never know it is us. There is a particular kind of humor buried in the fact that physics has now formally established a category of knowledge labeled permanently unknowable. Science has always pushed the boundaries of what is unknown, treating the unknown as a temporary condition, a gap to be closed by better instruments, more data, cleverer mathematics. The domain wall introduces something different, a result that is not unknown because we lack the tools, but unknown because the tools that could answer it are physically impossible within any universe. For the first time in scientific history, I don't know and I never will is not an admission of failure. It is a confirmed research finding, arrived at through rigorous theoretical analysis and observational constraint. It will appear in some form, in peer-reviewed journals. It will be cited. It is, by any measure, one of the most precisely established facts in modern cosmology. It is also almost certainly the strangest sentence ever to appear in a scientific abstract. This limit does not make science smaller. It reveals the true scale of what we are standing in front of. From Copernicus to Hubble, every century has delivered the same message in a different envelope. You are smaller than you thought, and the universe is larger, and the place you imagined you occupied at its center is not the center of anything. Nicholas Copernicus in 1543 moved Earth out of the center of the solar system. It took roughly a century and the combined force of Galileo, Kepler, and Newton to make that displacement stick in the scientific consensus. Then Harlow Shapley in 1918 showed that the Sun sits not at the center of the Milky Way, but in an unremarkable position, roughly halfway to its edge, one star among several hundred billion in no particularly privileged location. Then, Edwin Hubble in 1924 demonstrated that the Milky Way itself is not the universe, but merely one of countless galaxies, each containing hundreds of billions of stars, separated from each other by distances so vast that the entire history of human civilization fits inside the margin of error of their light travel times. Then the discovery of the cosmic microwave background in 1965 showed that even the observable universe, the full 46 billion light-year sphere of everything we can see, is just the finite bubble of causal contact available to us from our specific position in an almost certainly much larger space. Each displacement was resisted. Each was eventually accepted. Each felt, at the time of its announcement, like the final humiliation. Surely this is the last time science will tell us we matter less than we thought. It was never the last time. If the domain wall interpretation holds, and the multiverse is real, the displacement does not merely continue, it changes category. Every previous Copernican correction was a repositioning within the universe. Earth moved from the center to the periphery of the solar system, still in the same solar system. The Sun moved from the center of the galaxy, still in the same galaxy. The Milky Way became one of billions of galaxies, still in the same universe. Each correction was a change of address within the same building. The multiverse is not a change of address. It is the revelation that the building is one room in a structure with no known boundary, filled with an uncountable number of other rooms, each governed by different rules, none of which has any knowledge of or connection to ours. The entire observable universe, every galaxy, every star, every atom that has ever been part of any structure we have ever observed, is contained within a single bubble, one among an effectively infinite number, adrift in an eternally inflating background that makes the observable universe look like a single grain of sand on a beach that has no shoreline. That is not a change of address. That is the discovery that the concept of address requires complete rethinking. And here's where it becomes genuinely unsettling at a physical, not merely philosophical, level. The constants of physics that make our universe habitable, the precise mass of the electron, the specific value of the fine structure constant governing electromagnetic interactions, the exact strength of gravity, the cosmological constant sitting at just the right value to allow structure to form without collapsing or dispersing everything into emptiness. These values, in the framework of the string landscape and eternal inflation, are not the result of any design or necessity. They are the default settings of this particular bubble, the random outcome of how the inflaton field decayed when this specific region of the eternally inflating background nucleated into a stable universe. In most of the 10 to the power of 500 solutions of the string landscape, those constants take different values. Most of those values do not permit atoms. Most do not permit stars. Most do not permit chemistry, biology, cognition, or any process complicated enough to generate a question about itself. The overwhelming majority of the landscape is, by any measure of what we would recognize as complexity or life, sterile. We exist in this bubble not because it was made for us, but because it is among the vanishingly small fraction of bubbles where the constants happen to fall within the range that allows something as improbable as conscious matter to emerge. This is the anthropic principle, restated in its starkest form. We observe the universe. We observe because only in universes like this one does anyone exist to observe anything. Our presence is not evidence of purpose. It is a sampling bias built into the act of asking the question. If the physical constants of our universe are random, what does that change about what you think your life means? That question sits differently for different people, and science does not pretend to answer it, but it is worth sitting with it honestly. Because the alternative framing that the constants were chosen, tuned, designed for the emergence of life in mind, now has a rigorous competitor that requires no designer and no intention. Just an enormous number of bubbles, most of them empty of complexity, one of them containing everything we have ever known or will know. Consider a village, not a metaphor. Actually imagine a small village, a few hundred people, surrounded by farmland. For generations, the people of that village believe the village is the world. Their maps show the farms, the river, the surrounding hills. They know the names of every family. They have a complete picture of reality as they know it. Then a traveler arrives and tells them the village is one of millions on a continent, and the continent is one of several on a planet, and the planet is one of 8 orbiting a star, and the star is one of 400 billion in a galaxy, and the galaxy is one of 2 trillion in the observable universe, and the observable universe is one bubble among effectively infinite others in a multiverse with no known edge. Each step of that expansion is vertiginous. Each one feels like the final one. None of them has been. The village is still there. The people in it are still real. The relationships, the river, the names of the families, none of that becomes less true when the map gets larger. But the meaning of the world is permanently, irreversibly changed. It took humanity thousands of years to accept that Earth was not the center of the solar system. Thousands of years of resistance, persecution of those who said otherwise, institutional inertia in defense of a picture that felt cosmically necessary. Now science is announcing, with increasing observational support, that the entire universe is not the center of anything, that it is a local phenomenon in a structure so vast that the word vast requires its own revision. Humanity will adjust. It always has. The adjustment is just rarely comfortable, and it is never fast. But this smallness is not a tragedy. It is the necessary condition for understanding something much larger, and what that something is has never been clearly stated until now. Thomas Kuhn published The Structure of Scientific Revolutions in 1962, and the framework he described was so accurate that it immediately became the standard language for discussing how science actually progresses. The popular image of science as a steady accumulation of knowledge, each discovery adding cleanly to the last. The edifice of understanding growing taller brick by brick was, Kuhn argued, a myth. What actually happens is messier, more dramatic, and far more interesting. A dominant model forms. It works well. It generates successful predictions, organizes observations, guides research programs across decades. Then anomalies appear, small observations that do not quite fit, discrepancies that get noted in footnotes, results that get quietly set aside because the model is too useful to abandon over a few inconvenient data points. The anomalies accumulate, the footnotes multiply, the patches and adjustments required to keep the model consistent with new data grow increasingly baroque. Then a threshold is crossed. The weight of unresolved anomalies becomes too great to ignore. The model enters crisis, and a new framework emerges that reorganizes everything, not just fixing the anomalies, but reordering the entire conceptual landscape in a way that makes the old model look, in retrospect, like a useful approximation of a deeper truth rather than the truth itself. Kuhn called these moments paradigm shifts. Cosmology has produced 4 of them. The evidence now accumulating around the domain wall signal suggests the 5th is approaching. In 1543, Nicholas Copernicus published De Revolutionibus Orbium Coelestium and proposed that Earth orbits the Sun rather than the reverse. The model he replaced Ptolemy's geocentric system had been the dominant framework for 1400 years. It was not simply a cultural preference or religious dogma, though both were involved in its defense. It was a genuinely functional predictive system, capable of calculating planetary positions with reasonable accuracy using an elaborate system of epicycles and deference. It worked, within its domain, but the anomalies had been accumulating for centuries, the irregularities in planetary motion that required ever more complex epicycles to explain, the persistent mismatches between prediction and careful observation. Copernicus reorganized everything around a different center. The anomalies dissolved. In 1915, Albert Einstein published the general theory of relativity and replaced Newton's conception of gravity as a force acting instantaneously across empty space with a description of gravity as the curvature of spacetime produced by mass and energy. Newton's framework had been dominant for 230 years and remained extraordinarily accurate for most practical purposes. But the anomaly of Mercury's orbital precession, a slow rotation of Mercury's elliptical orbit that Newton's equations could not fully account for, had been accumulating since the 1800s. Einstein's equations explained it exactly, without adjustment. Space and time were not the fixed, absolute background Newton assumed. They were dynamic, curved, participant in the physics they described. In 1929, Edwin Hubble demonstrated that the spiral nebulae scattered across the sky were not clouds of gas within the Milky Way, but independent galaxies, each containing hundreds of billions of stars, and that they were receding from us at velocities proportional to their distances. A static, eternal universe, the model Einstein himself had initially assumed when applying his equations to cosmology, was replaced by an expanding universe with a definite beginning. The Big Bang was not an idea Hubble proposed. It was the unavoidable implication of the recession velocities his observations revealed. In 1998, Saul Perlmutter, Brian Schmidt, and Adam Rees, studying the brightness of Type B Ia supernovae at cosmological distances, found that the universe's expansion is not slowing under gravity as every prior model assumed. It is accelerating. Something dark energy, the cosmological constant, call it what you will, is pushing the universe apart with increasing force. This discovery, which earned the Nobel Prize in 2011, overturned an assumption so fundamental that it had not even been articulated as an assumption. Everyone had presumed that gravity dominated the universe's long-term dynamics. It does not. Each of these four revolutions was preceded by exactly the pattern Kuhn described. Each was resisted fiercely before it was accepted. Einstein, who revolutionized physics twice in a single decade, famously declared that God does not play dice when confronted with the probabilistic implications of quantum mechanics, a theory whose foundational anomalies his own work had helped expose. He spent decades attempting to construct a deterministic alternative. He never succeeded. Late in his life, the evidence against the deterministic picture he preferred had become overwhelming. The man who shattered one paradigm spent his final years unable to accept the next one. Science does not spare its heroes from the psychology it imposes on everyone else. The resistance is not irrational. It reflects something real about how deeply a successful model embeds itself in the structure of thought. You do not simply swap out a framework the way you swap a flat tire. A paradigm is a way of seeing. Changing it means changing what counts as a question worth asking, what counts as an acceptable answer, what anomalies register as important, and what gets dismissed as noise. The transition is disorienting in a way that purely technical developments are not. The anomalies now pressing against Lambda-CDM, the Hubble tension, the premature formation of massive early galaxies, the cosmic Webb asymmetry, the CMB cold spot, and now the domain wall lensing signal with its three-way spatial alignment follow Kuhn's pattern with uncomfortable precision. Each anomaly, in isolation, generated footnotes. Together, they are generating a crisis. The patches required to keep Lambda-CDM consistent with all of them simultaneously are becoming too numerous and too contrived to sustain the framework's credibility as a fundamental description of reality. The domain wall signal is the latest and largest anomaly, but it is also qualitatively different from the ones that preceded it. If confirmed, it does not merely require revising the model, it requires expanding the ontology, the catalog of things that exist beyond the boundaries of the single universe that all four previous revolutions assumed as their shared stage. Every prior cosmological revolution changed our position in the universe. Copernicus moved Earth. Shapley moved the Sun. Hubble multiplied the galaxies. The accelerating expansion changed the fate. But all of them were rearrangements within a single universe, a single space-time, a single Big Bang. The domain wall, if real, announces that the universe itself is not the totality of existence. It is a room, a bubble, one solution among an effectively infinite number, physically adjacent to others, separated from them by boundaries that have observable shadows. Previous revolutions changed the map of the house. This one establishes that the house is a single room in a building with no blueprint and no known limit. Of the four great cosmological revolutions, which do you think was the hardest for humanity to accept? The question is worth sitting with. Because whatever your answer, the fifth revolution's being signaled by the domain wall asks something harder than any of them. Not just, where are we, or how big is the universe, but how many universes are there? And does the answer have any bearing on why the rules that govern ours are the way they are? Science has a reliable tradition worth acknowledging. The moment a theory is declared the final, complete, triumphant description of reality is almost invariably the moment the data begins preparing its rebuttal. Newton's mechanics were considered essentially complete in the late 1800s. The Michelson-Morley experiment was published in 1887. The Standard Model of Particle Physics was completed in the 1970s and immediately began accumulating anomalies that have not been resolved in 50 years. Lambda-CDM was declared the concordance model in the early 2000s. The first JWST images were released in 2022. The pattern is not a failure of science. It is science working correctly. Every final answer is a better question in disguise. If this is the fifth revolution, its pioneer is not Einstein or Hubble. It is a $10 billion telescope in orbit around Earth right now. $10 billion, 25 years of development, 344 single-point failure modes, individual mechanisms, each of which, if it malfunctioned during deployment, would have ended the mission completely and irreversibly. The James Webb Space Telescope is the most mechanically complex scientific instrument humanity has ever constructed. Not the most expensive in absolute terms, not the heaviest, not the one with the most computing power, but in terms of the precision required, the tolerance for error, and the number of sequential operations that all had to succeed without a second chance. Nothing built before it comes close. 344 ways it could have died. It survived all of them. James Edwin Webb was born in 1906 in Tally Ho, North Carolina, and died in 1992, having spent the most consequential years of his career running an agency he did not found, pursuing a goal he did not originate. Under political pressure, he managed with a skill that most scientists who came after him have never fully appreciated. Webb served as NASA administrator from 1961 to 1968, the years that encompassed the Mercury and Gemini programs and the early Apollo missions. He presided over the agency during the period when putting a human being on the moon was the single most visible scientific and political objective of the United States government. The pressure to concentrate every available resource on that goal was enormous. Congressional funding depended on lunar success. Public attention was directed at lunar success. The entire cultural weight of the space race pointed toward the moon and nothing else. Webb pushed back, not against the lunar program, which he supported and managed effectively, but against the argument that the moon was all that mattered. he insisted on maintaining a robust program of scientific research alongside the human spaceflight missions funding astrophysics, planetary science, and fundamental research into the nature of the universe at a time when those programs were the most politically vulnerable items in the NASA budget. He was criticized for it. The criticism was sometimes pointed. His response, in various recorded forms, was essentially consistent. Landing on the moon was a demonstration of capability. Understanding the universe was the reason capability mattered. The space telescope that bears his name was not named for Webb because he was a physicist or an astronomer. He was neither. It was named for him because the people who fought to build it recognized that without his insistence on the value of pure scientific inquiry during the years when that insistence was most costly, the institutional culture that produced JWST might not have survived long enough to conceive of it. The telescope launched on December 25, 2021, from the Guyana Space Center in Kourou, French Guyana. The launch was the easy part. What followed was 30 days of deployment, so technically demanding that engineers referred to the period informally as 30 days of terror, a sequence of over 300 major deployment steps, including the unfolding of the sun shield to the size of a tennis court, the deployment of the secondary mirror on its support structure, and the final unfolding of the primary mirror's 18 hexagonal, gold-plated beryllium segments into their operating configuration. Each step had to execute correctly in the specific sequence required. There was no crew aboard. There was no option to send a repair mission. Every mechanism had been tested on Earth, but space is not a laboratory, and the combination of vacuum, temperature extremes, and zero gravity produces conditions no ground test fully replicates. After 29 days, the telescope reached its operational position at the second Lagrange point, approximately 1 million miles from Earth in the direction away from the Sun. The first full-color science images were released to the public in July 2022. They were, by any reasonable aesthetic and scientific measure, extraordinary. In 3 years of operation, Webb has done the following, found fully mature: massive galaxies existing when the universe was less than 500 million years old, a finding that directly contradicts Lambda-CDM's predictions about structure formation timescales. Detected carbon dioxide in the atmosphere of a gas giant orbiting another star, the first direct atmospheric chemistry measurement of an exoplanet. Imaged dust structures around comets in our own solar system with a clarity that revealed features invisible to all prior instruments. Observed stellar nurseries in nearby galaxies at resolutions that have rewritten the observational record for star formation physics, and now a gravitationally anomalous lensing signal from an empty region of space whose geometry matches the theoretical prediction for a domain wall between two universe-scale bubble structures. Galileo Galilei built his first astronomical telescope in 1609, a crude instrument by modern standards, capable of magnifying objects roughly 20 to 30 times, and pointed it at Jupiter. What he saw were 4 points of light orbiting the planet, appearing and disappearing as he watched over successive nights. They were moons. Jupiter had moons. This was not predicted by any geocentric model of the cosmos. It was not supposed to exist. It was the first direct observational evidence that not everything in the sky revolves around Earth. And it was found not by a mathematician working equations, but by a man who built a better instrument and looked. JWST is a better instrument by a factor that makes Galileo's telescope look like a children's toy in comparison. And the thing it may have found is not merely evidence that Jupiter has companions, or that Earth moves around the Sun, or that galaxies exist beyond our own. It may have found evidence that our universe has a neighbor, that there is something on the other side of a boundary, billions of light years wide, pressing against the fabric of our space-time from outside, leaving its shadow in the light that passes near it. If you had spent 25 years designing this telescope, Would you have imagined it would find this? The engineers and scientists who built Webb were hoping to see the first galaxies, the most distant stars, the atmospheres of potentially habitable worlds. Nobody wrote, "Detect the boundary of the observable universe with another universe" in the science requirements document. Nobody included it in the mission objectives. The greatest discovery in the telescope's young history may turn out to be the one that was never on the list. Webb was designed to look at the farthest thing it could find, the most distant light, the oldest structures, the furthest reach of the observable universe. It looked as far as physics allowed, and it may have found not the beginning of what exists, but the edge of what we are allowed to know. The most important thing it has observed might be the patch of sky where nothing was supposed to be. The instrument built to see everything may have found the thing that marks the end of seeing. But however much Webb finds, the final question is not, what can we see? It is, why is there something here to see at all? The decade running from 2025 to 2035 will produce more observational data about the large-scale structure of the universe than every prior century of astronomy combined. Not slightly more, not meaningfully more by orders of magnitude, a flood of information so large that the bottleneck will not be the telescopes collecting it, but the human minds is capable of making sense of what comes back. This is not a prediction. It is already happening. The Vera-C Rubin Observatory began scientific operations in 2025. The Euclid Space Telescope is mapping 1/3 of the sky in 3 dimensions. The Nancy Grace Roman Space Telescope launches in 2027. Webb continues. Every one of these instruments is pointed, in some configuration, at the same fundamental questions that the domain wall signal has forced back to the center of cosmological inquiry. The golden age of observational cosmology is not coming. It is here, running. And the data stream has barely started. What that data will return, no one knows exactly. But the shape of the possible answers is already clear. There are 3 of them, and each one, in its own way, ends the same way with cosmology permanently, irreversibly changed. The first scenario is confirmation. The domain wall signal survives. Vera Rubin's 37 billion galaxy catalog shows a coherent spatial distortion in the distribution of matter consistent with the estimated position and scale of the boundary. Euclid's weak lensing maps show an anomalous deflection field in the same sky coordinates, extended and flat, in a way that no conventional astrophysical structure produces. Roman maps the full geometry of the structure across angular scales that Webb cannot cover in a single program. The polarization analysis Webb proposed returns the rotation signature that domain walls and only domain walls produce. The independent measurements converge. The confidence crosses 5 sigma, then 6. At that point, the physics textbooks do not get revised. They get rewritten from the first chapter. Every equation that assumes a single universe as its backdrop requires renegotiation. The standard model, built on the assumption that the physical constants it encodes are fundamental rather than contingent, needs a new interpretive framework that accommodates the possibility that those constants are local, the specific outcomes of how one particular bubble, nucleated in one particular region of an eternally inflating background. Dark energy acquires a physical address. String theory acquires its first empirical validation. The Nobel Committee convenes. And humanity officially learns, through the slow machinery of peer review and scientific consensus, that we are not alone, not in the biological sense that science fiction imagined, but in the cosmological sense that is stranger and more vertiginous than any of that fiction managed to anticipate. We are not alone in the sense that another universe exists, adjacent to ours, pressing against our space-time across a surface billions of light-years wide, with no possibility of communication, no shared physics, no common history. neighbors in the most absolute sense of the word, permanent, unreachable, confirmed. The second scenario is falsification. The signal does not survive. Vera Rubin maps the region and finds no coherent, large-scale distortion. Euclid's lensing data shows nothing anomalous at the relevant coordinates. The 4.7 sigma result from Webb turns out to be a particularly convincing statistical fluctuation, or a systematic instrumental effect that only emerges under specific observational conditions, or the signature of a physical phenomenon that exists entirely within our universe and has no prior theoretical description. This scenario sounds like a failure. It is not. If the domain wall interpretation is wrong, something else produced that signal. Something real. The statistical analysis rules out pure noise. That something, whatever it turns out to be, is a phenomenon that does not appear in the current catalog of known physics. A new form of gravitational lensing, an undetected class of compact object, a property of large-scale structure that no existing model predicted. Any of those alternatives is, by itself, a historic discovery. The history of cosmology is full of anomalies that turned out to be something other than what the most dramatic interpretation suggested, and what they turned out to be was still worth finding. The Bicep 2 signal was not primordial gravitational waves. It was interstellar dust behaving in ways that existing dust models had not fully captured. That result improved dust models and refined CMB polarimetry in ways that have since mattered enormously. Falsification does not close a door, it opens the correct one. The third scenario is suspension. The signal is real. The domain wall interpretation cannot be ruled out, but the structure, if it exists, sits at a distance and scale that the instruments of this century can characterize only partially. Vera Rubin sees something, but cannot resolve it definitively. Euclid's data is consistent with the domain wall hypothesis, but also consistent with 2 or 3 alternative explanations that cannot be separated at current sensitivity. Roman maps a portion of the geometry, but not enough to constrain the models to a single answer. The question is passed forward. The children currently in 8th grade, 12 and 13 years old, doing homework about the solar system and the periodic table, will be in their mid-30s when the Vera Rubin dataset reaches full depth, when the next generation of space telescopes beyond Roman begins returning data, when the computational infrastructure needed to process cosmological surveys at that scale has matured enough to run the analyses that settle the question. Those children will be the ones who sit with the data, write the papers, and arrive at the conclusion. They do not know this yet. They are doing homework. This is exactly what the generation of Hubble's contemporaries did not know about themselves. Edwin Hubble demonstrated in 1929 that the universe was expanding and that the observable universe contained billions of galaxies rather than a single one. The people who were alive in that decade, reading the papers, attending the lectures, absorbing the cultural shock of a universe suddenly made a billion times larger, did not know they were living through the permanent transformation of cosmology. They knew something exciting was happening. They did not know that 100 years later, physicists would still be tracing the implications of what Hubble's redshift measurements implied. Future cosmologists will look back at the 2023 to 2027 period the way we look back at the 1920s. They will read the papers from this era and feel the particular combination of vertigo and sympathy that comes from watching people stand directly in front of a revelation they cannot yet fully see. The data was there. The signal was in the noise. The question was already formed. The answer was a decade away, and the people closest to it were the least able to recognize how close they were. This is not a failure of intelligence. It is the normal condition of being at the edge of knowledge rather than looking back at it from a safe distance. If you were a scientist working in the next decade, which project would you want your name on? The question is worth sitting with seriously, because the options are genuinely extraordinary. Working on the Vera-Rubin data pipeline means handling the statistical analysis of 37 billion galaxies, looking for the spatial fingerprint of something that has never been observed before. Working on Roman's domain wall mapping program means designing the observational strategy for the first comprehensive geometry measurement of a structure billions of light-years in extent. Working on the theoretical side means building the mathematical framework that will either validate or replace the domain wall interpretation when the data arrives, constructing the models that will be tested against the most consequential data set in the history of cosmology. The graduate students beginning their doctoral programs right now will defend their dissertations into the middle of this confirmation window. Some of them are already working on the relevant data. They are 22, 23 years old. They are processing Webb observations and building simulation pipelines and writing sections of papers whose implications they are probably too close to fully appreciate. Future cosmologists will look at the 2020s and think they were standing right in front of the answer, and they did not know it. The same thought we have about the people of 1900, standing at the edge of relativity and quantum mechanics without knowing that the two revolutions that would define the next century were already visible in the anomalies accumulating in their data. The pattern repeats. It always has. The people inside the moment rarely see the shape of it clearly. That clarity is a privilege of retrospect. What is different this time is the speed. The tools are faster, the data richer, the computational infrastructure more capable of handling complexity at scale. The gap between anomaly and resolution, which took decades for Copernicus, decades for Einstein, decades for Hubble, may compress to years. The answer, whatever it is coming within living memory of the people who first saw the signal. Cosmology will not look the same on the other side of this decade, not in any of the three scenarios, not even close. But before that future arrives, there is something none of us were prepared to hear. Eternal inflation produces bubble universes. Each bubble nucleates with a different set of physical constants, different electron masses, different gravitational strength, different values for the cosmological constant. The mathematics is clear. The logic is internally consistent. The domain wall signal, if confirmed, provides the first observational evidence that the framework is physically real rather than mathematically elegant speculation. All of that is the answer. The answer science has been building toward through every section of this story, every eliminated hypothesis, every converging anomaly, every layer of theoretical framework stacked carefully on top of the last. Now, dismantle it. Not because it is wrong, because it is incomplete in a way that the answer itself conceals. Eternal inflation does not self-generate. It does not arise from nothing, create its own conditions, bootstrap itself into existence from a prior state of non-existence. For eternal inflation to operate, for the quantum field to fluctuate, for some regions to decay while others keep inflating, for bubble universes to nucleate continuously across an expanding background, there must be something for inflation to operate in, a substrate, a set of rules governing how fields behave, a prior physical context within which the inflaton field exists and evolves according to equations that had to come from somewhere. That prior context is the inflaton field itself. And here's the problem. The inflaton field, the quantum field whose energy drives inflation, whose quantum fluctuations determine whether a given patch of the eternally inflating background decays into a bubble universe or keeps expanding, is not explained by any existing physical theory. It does not appear in the standard model of particle physics, which describes every known particle and every known force with extraordinary precision, and says nothing about what drove inflation. String theory produces the landscape of possible universes, but does not, in any complete and agreed-upon formulation, derive the inflaton field from first principles. It exists in the equations of inflationary cosmology as an input, a given, an assumed starting condition whose origin the equations do not address. Physicists know what the inflaton field does. They can describe its behavior in mathematical terms of extraordinary sophistication. They cannot tell you what it is, where it came from, or why it exists rather than not existing. The inflaton field is the foundation on which the entire edifice of eternal inflation, bubble universes, domain walls, and the string landscape rests. It is also the one thing in the entire framework that the framework itself cannot explain. It sits at the bottom of the theoretical structure the way a foundation sits beneath a building load-bearing, essential, and, in this case, unexplained by anything more fundamental. Which means the answer loops back into a question, not a small question, not a technical question that better mathematics or more powerful telescopes will eventually resolve. The question that the inflaton field points toward is the oldest question in philosophy, dressed in the language of modern physics, and it has not gotten any easier with the century of scientific progress that has been built on top of it. Why is there inflation? Why is there a quantum field at all, operating according to mathematical rules, embedded in a space-time that had to exist for the field to exist in? Why is there physics? Why is there mathematics? The abstract structure that describes physics with a precision that has never been adequately explained, rather than the absence of any structure at all. Why is there something rather than nothing? That question does not have a physical answer, not because physics has not yet found one, because the question is not a physical question. It is a question about the existence of the conditions that make physics possible. Physics describes what happens inside a universe, or inside a multiverse, or inside an eternally inflating background. It does not and cannot, by its own rules, describe why any of those things exist rather than not existing. The domain wall is not the answer to the deepest question. It is evidence that the deepest question is deeper than we thought. This is the structure that the story has been building toward, and it is worth stating clearly because it is easy to miss in the accumulation of technical detail. We began with a telescope finding a signal that could not be explained. We eliminated every conventional explanation. We arrived at a framework eternal inflation, bubble universes. The string landscape that accounts for the signal, resolves the anomalies, and offers the first experimental evidence for the theoretical architecture that has dominated fundamental physics for decades. That framework is genuinely extraordinary. It may be correct. The domain wall may be real, the neighboring universe may be there, and cosmology may be on the edge of its fifth and largest revolution. And none of that is the final layer. The final layer is this: the framework that explains the multiverse does not explain itself. Every answer in the chain bubble universes are produced by eternal inflation. Eternal inflation is driven by the inflaton field. The inflaton field obeys quantum mechanical rules. Quantum mechanics operates within space-time, terminates at a foundation that the chain cannot reach below. Why does the inflaton field have the properties it has? Why does quantum mechanics have the rules it has? Why does mathematics describe physical reality with the precision? It does a correspondence so exact that equations written on a blackboard in the 1900s predict phenomena discovered by telescopes in the 21st century. Why is there a universe or a multiverse at all? We are not approaching the final answer. We are discovering that the final question is larger than any answer we have ever thought to reach for. Domain wall is not the boundary of the universe. It is the boundary of a particular kind of knowing. The lensing signal that Webb captured, the shadow of a wall billions of light years wide, is not a window into ultimate reality. It is a marker, the furthest point to which physics can point and say something is there, and we can describe its shape. Beyond that point, in every direction that matters, the direction of origins, the direction of why, the direction of the question that precedes all physical questions, the instruments stop working. Not because they are not powerful enough, because the question they would need to answer is not a question about things that exist in space and time. The James Webb Space Telescope may be looking at the wall of another universe, but the question that no telescope will ever answer, why there is a wall there to look at, why there is light that bends around it, why there is a universe containing a telescope capable of noticing, that question belongs to us, to whatever it is that we are, in the narrow band of conditions that allow something as improbable as conscious matter to arrange itself into the shape of a creature that looks at the sky and asks why. We may be the only thing in this universe, in this bubble, that is genuinely asking. And the asking itself, the fact that the universe has, in at least one small corner of one bubble, produced something that turns around and wonders about its own existence, may be the strangest fact in all of cosmology. Stranger than the domain wall? Stranger than the multiverse? Stranger than 10 to the power of 500 universes with different physics? The strangest thing is not that the universe is so large. The strangest thing is that it knows it is.